All right, so we're going to look at our last section for the week, which is 4.2. We're going to split it into two parts. We'll do half today, half tomorrow. Okay, so yesterday we talked about this idea that there could be a hole in the graph. Okay, and that's going to happen today. So if you have a rational function, okay, you got to check if the numerator and denominator have common factors. If they do, you could have a hole or a discontinuity there that you can't see on the calculator. Asymptotes are very easy to see on the calculator because you see it, spiking up to infinity for like a vertical asymptote, or for a horizontal asymptote, you see it leveling out. But if you have a discontinuity because of a hole, you can't see that on the graph. You just have to know from the equation using algebra that it's there. Okay, here's a function I'm going to graph. I'm going to graph x minus 1 divided by x minus 1. Okay, what do you get when you divide two things that are the same? 1. So this is basically going to look like this. F of x equals 1. It's going to be a horizontal line at 1. Almost. Okay, so let's graph it and see what happens. X minus 1 divided by x minus 1. Okay, if you want to be safe, just put it in parentheses so it'll handle any kind of order of operations without an issue. Do a standard window. And as I said, it pretty much looks like a horizontal line, y equals 1, but it's not quite. Okay, because you have to remember the way that this was generated, the denominator couldn't be a certain value. What can't the denominator, or what can x not be? Yeah?
X can't be 1 because the denominator would then equal 0, making it undefined.
So x can't be 1. So watch what happens if you type in any value you want, other than 1. You always get 1. If you try 5, the top would be 4, bottom would be 4. 4 divided by 4 is 1. Any value will give you 1, except if you type in 1. You get an error. Okay, so what that basically means is there's a hole in the graph. Right? Can't quite get exactly on it, but right around there. There's a small hole. 0.9 repeating, that'll work just fine. You can go as close to 1 as you want. You just can't type, see, I'd even round it to 1, but you just can't type in 1. Right? Be careful when you look at something like that, because when it rounds it, you might think you can type in 1, but it's really 0.9 a bunch of times. All right, let's try this one. Okay, x minus 1 squared divided by x minus 1. What is this one going to look similar to? Think of it as x minus 1 squared divided by x minus 1 to the first. When you divide two things with the same base, what do you do with the exponents? You subtract them. Keep the base the same. So this is basically going to look like x minus 1 to the first power. That's a line with a slope of 1, y-intercept at negative 1, but there's going to be a hole in it again. Okay, where is the hole going to be? Right where it is now when x is 1. Okay, so if you still have it typed in, you can just go like that. There's your line. Looks like it has a slope 1, y-intercept negative 1, but there is a hole where it's crossing the x-axis. Right? Any question on that? Right, so it'd be kind of tricky. I wouldn't ask you this, but if I asked you, what's the x-intercept of this? That's kind of a tricky question because there's a hole right where the x-intercept would be. So for that, I would say there is no x-intercept. It never really crosses the x-axis because there's a hole there. All right, and that's kind of a debatable question, but I won't ask you something that's tricky like that. I just want you to understand when you can get a hole in your graph. Now, if I just change one thing slightly, change this, change one of the number 1s to a different number. Try making it x minus 2 squared. Well, you're still going to have something funny happen at 1. It's still, you can't plug in 1. But now it's not going to be a hole. You're going to get asymptotes. Okay, in this case, you're getting a slant asymptote. There's a line in here that these edges are getting closer and closer to as they head towards infinity. Okay, so just by changing that one small number, we've totally changed the look of the graph. Completely. Okay, so in the previous examples, there was no vertical asymptote. We had a removable discontinuity, which basically means you can, if you could redefine the function at that one particular point, just that one point, then everything would be fine. Okay, that's the idea of a removable discontinuity. When we have an asymptote, that's not a removable discontinuity. There's no way I can fix that picture and by just redefining one single point and making it a connected graph. With the other ones, yes, I could. I could make them connected just by redefining one single point. All right, so suppose we had two polynomials. Okay, I've just written them out, with using variables and coefficients that are letters. But this just represents two polynomials divided. Okay, the next thing we're going to study is what's called an end behavior model. Okay, what an end behavior model does is it predicts what the function is going to look like way out when x gets big. Okay, an end behavior model is doesn't predict like what's going to happen near the origin or when x is small. It predicts what this function is going to do when x gets huge. Okay, that's what an end behavior model is. All right, it's used to predict what's going to happen when x gets really, really big. Right? Because when you have a polynomial like that, when x gets really, really big, there's only one thing there that matters. That. Nothing else is really going to make a difference. Okay? So if x is 1 billion, if you take 1 billion and raise it to the 4th power and then triple it, and then you do these other terms are going to be so small compared to the first term, they're not even really going to make a difference when x gets huge. Now, when x is small, absolutely, they make a big difference. But an end behavior model isn't really used when x is small. It's used when x is big. So in the rational function I have above, if you want to know the end behavior model for the numerator, it's basically just the term with the highest degree. That's the term that's going to control everything. Okay, and we might have mentioned the idea of end behavior model before. Not sure if we did in an earlier chapter. So we're seeing it again if we did. Right? And if you wanted to know the end behavior model for the denominator, it would be that term. That term alone is going to predict what the denominator is going to do when x starts to get huge. Nothing else really matters. Now, if you're interested in finding all the little twists and turns that the graph is going to take, okay, then we need everything. But if you just want a general idea of what it's going to do, that's what the end behavior model is. So if you want an end behavior model that represents the rational function, not just the top and the bottom separate, take the end behavior model for the top, take the end behavior model for the bottom, and divide them. And that's the end behavior model for the entire rational function. Now, notice here we're dividing a sub n and b sub n. Those will be numbers. They're coefficients. But then we have x to the n divided by x to the m, dividing two things that have the same base, x and x. So what can we do with the exponents on x? Now, I think we did this rule earlier as well. We can subtract them. simplify our end behavior model as dividing the coefficients. Okay, we'll see what those are in a minute. We'll do a problem. And then the power that you have is x to the n minus m. And that's the end behavior model for your rational function. Okay, another way to think of it is if you graph the end behavior model and you graph the original function and you zoom way out, they're probably going to look identical. Okay, so you could try that sometime. Try setting your x min and max to like 5,000 and your y min and max, negative 5,000 to 5,000. Graph two different functions, use one with the end behavior, one with the original, and they'll probably look the same. So what the end behavior model is good for is finding your horizontal asymptotes. Because to find a horizontal asymptote, you have to look at what's happening as x gets huge. Well, that's exactly what the end behavior model tells you. It tells you what's going to happen when x gets huge. Okay, so I will be using the end behavior model to find the horizontal asymptotes. Okay, let's just start with the end behavior model of the numerator. Brandon, what's the end behavior model of the numerator? 2x squared. Yep. Divided by, Nick, what's the end behavior model for the denominator? 3x cubed. And if we simplify that, can anybody tell me what that will simplify to? It's going to have a 2/3 in there, but I just want to know the power of x. Yeah?
X to the negative.
Yeah, you can write it as x to the negative 1. Anybody else tell me, how can I write that without a negative exponent? Yeah?
1 over x.
Okay.
2/3.
So 2/3 times 1 over x, which would be 2 over 3x. Okay, so that's my end behavior model. Now, if you plug in a really big number for x, figure out what this fraction would get very close to, and that's your horizontal asymptote. Okay, so what would happen to this fraction if I plug in a huge number for x, and I do 2 divided by 3 times something huge? This fraction is, as x keeps getting bigger and bigger, what is this fraction going to get closer and closer and closer to? It's never going to reach it, but it'll get very close to it.
0.
It's going to get very close to 0. Okay? And that's where my horizontal asymptote is. Remember, horizontal lines are always y equals, vertical are x equals. Okay, so you can use your end behavior model, let x get huge, let it go towards infinity, and that'll tell you your horizontal asymptote. And if you do negative infinity, you get the same thing. 2 divided by 3 times a huge negative number, it's still 0. Okay, any questions on finding an end behavior model or horizontal asymptote? Okay, the other thing you have to be careful of is make sure if I don't have it in descending order, meaning highest to lowest exponents, you have to look through all the terms and find the highest degree exponent. Okay, these are in order. Okay, what's our end behavior model here? You don't even have to simplify it yet. I'd like to actually know what it would be before you simplify it. Oh, Justin?
I didn't get the question.
What would be the end behavior model?
2x.
Yep, divided by
X to the 4th.
3x to the 4th. And can you simplify that?
2/3.
2/3. There's your end behavior model. So what's my horizontal asymptote? As x gets really, really big, what's going to happen to this fraction? It's going to stay the same. There is no x in it. So as x gets really big, y approaches 2/3. Okay, so you might be starting to get an idea of what kind of exponents you need to have in order to get, say, a 0 horizontal asymptote. And then what kind of exponents you need to have to get a horizontal asymptote that's not a 0. What kind of does anybody think they could answer that? What kind of exponents do you need in order to get a horizontal asymptote that doesn't equal 0? I want to just compare the two exponents in the leading terms. Yeah?
You have to have two exponents that don't subtract to equal 1.
Okay, what do you need to have then?
You need to have two exponents that would add or subtract to give you an integer other than 1.
Not quite in this. Think of it as specifically in this case what happened, what kind of exponents we had on the leading terms.
They have to be to the same power.
Yeah, they're the same. Anytime your exponents on the leading terms are the same, the x's are going to cancel out and you're going to be left with numbers, assuming that these aren't zeros. Okay, you're going to be left with two numbers. That will be your horizontal asymptote. Anytime that the exponent in the denominator is bigger than the one in the numerator, you're always going to get a horizontal asymptote at 0. Okay? It doesn't matter if it's 3x to the first power, 3x to the second power. If you've got an x in the bottom, it's going to make the bottom huge. And then anytime you divide by something huge, you get 0. Okay? Now, if you had the other case, we haven't looked at where the numerator is bigger, then we don't have a horizontal asymptote. If your numerator is bigger, you're going to end up with an x not left over in the bottom, but in the top. That means your numerator is going to get huge. And if the numerator is approaching infinity, I don't care what you divide by, you're going to be dividing by a number. Infinity divided by a number, it's still infinity. So there would be no horizontal asymptote in that case. Right, so we will talk about some problems like that. Okay, what we're going to do is do some sketches specifically of a certain type. We're going to sketch when the degree of the numerator is less than or equal to the degree of the denominator. Okay, when that's not true, when the degree of the numerator starts to get bigger, we have to do a few different things to sketch it. Some other things we need to look at. Okay, so what you want to try to do first that can be helpful is find your intercepts. Now, keep in mind, not every graph has x and y-intercepts. It is possible that a graph never crosses one of the axes, or even both. So, if that's possible, find your intercepts. Another thing that's going to help us to make a sketch is to know where the vertical asymptotes are. How do you find vertical asymptotes? Find the zeros of the denominator. And there's only one catch to that. When could you have a 0 in the denominator, but it doesn't end up being a vertical asymptote? And those are the first two things we looked at today. Everybody tell me when that would happen. When could you have a 0 in a denominator? Okay, you find a number for x, it makes the denominator 0, but it's not a vertical asymptote. It only happens in one special case.
When there's a hole.
And what would cause there to be a hole?
There was factors in the denominator that would cancel out.
Yes, if you have factors in the numerator and denominator that would cancel out, then you don't get a vertical asymptote, you get a hole. Okay, so keep that in mind. Right, next thing that's helpful is to find the end behavior model. Why? Because that tells us what's going to happen to our graph as x starts to get huge. So we can kind of see where should we be, drawing it to. And then what we'll do is after we have horizontal asymptotes, In step 4, we're going to evaluate the function on each side of a vertical asymptote. Generally, when you have a vertical asymptote, one side near the asymptote is heading towards infinity, and the other side is heading towards negative infinity. Now, it is possible they could both head towards infinity. If you had a vertical asymptote, you can get a picture like this. So we do need to check. So what we'll do is if we had a vertical asymptote at 2, we would check what's happening at 1.99 and what's happening at 2.01. Check what happens on each side of the asymptote. And then we can confirm our picture with a calculator. We can double check and see how we did with our sketch. Okay, so we're going to start by trying to sketch this. X minus 1 divided by x squared minus x minus 6. Right, before we even sketch it, there's something I would do here. And if we do this, it's going to help us with some of the steps. I mean, this is okay to do some of the steps that we need to do, but to do some of the other steps, we're going to have to do something with the denominator. Nick?
Factor.
Yeah, we're going to factor it. What would that factor as? Well, start with your first term in each set of parentheses.
They would both be x.
Both be x. What about your signs?
Negative and positive.
Yeah, you got to have one of each because you're trying to multiply two things together to get a negative. And two numbers that multiply together to give me 6. And they're going to have to subtract to give me 1. Let's check it. X squared. Take away 3x plus 2x. That's good. Yep, that's good. Okay, keep both of these because they're both handy to have. All right, let's go through our steps. Okay, find your x and y-intercepts. Okay, to find your x-intercept, that's when you let y equal 0. Okay, so that's when you'd have a 0 right there on that side. So what's the only way you could make this fraction 0? If what part of it is 0? Yeah? If the numerator is 0. Okay, so what value would make the numerator 0? That's the question we need to ask. So set the numerator equal to 0, and you get x equals 1. That's your x-intercept. Okay, so we can graph that. Just plot that point. It's going to cross the x-axis right there. Okay, let's find our y-intercept. Okay, how do you find a y-intercept? Yeah? Yeah, you set x equal to 0. So we could use either one, it doesn't matter. 0 minus 1 is negative 1 over 0 minus 6. So my y-intercept is 1/6. Okay, so it's going to cross the y-axis pretty close to that point. Since they're so close, it doesn't really give me a good picture. So we need some more stuff. Let's find the vertical asymptotes. This is why I had you factor it. There's two vertical asymptotes here. And there's no common factors. I wanted to point that out as well. No common factors. Okay, what are my two values that would give me 0 in the denominator? Yeah?
It would be negative 2 and 3.
Yep, so we have x equals negative 2 and 3. Okay, sketch your asymptotes in as vertical lines. So put one at negative 2 and put one at positive 3. Oops. So about right there and there. So we got our vertical asymptotes. Okay, next let's get the end behavior model, and that will help us to get the horizontal asymptote. Okay, end behavior model. This is where I'd go back to the original because I can see the highest powers. It's x divided by x squared. And that's going to simplify to 1 over x. Now I can get my horizontal asymptote. What happens to the fraction 1 over x as x approaches infinity? About Sam? What happens to the fraction 1 over x as x approaches infinity?
It approaches 0.
It approaches 0. Good. So we have a horizontal asymptote at 0. Okay, so all these green lines are lines that our function is going to get closer and closer to, but never touch. Okay. Last thing we need to do is evaluate the function near each side of the vertical asymptote. Okay, so now I need to actually, I would just type it in and let's use second table to do that. So you've got x minus 1. Let's see, x minus 1 divided by x squared minus x minus 6. Okay, let's start with negative 2. Okay, we know that's an error. That's our asymptote. So what would be a value very close to negative 2? Let's start on the left side. The left side of negative 2. Yep. So I want to be somewhere like around here.
Oh, I'm sorry, negative.
Okay, that's going to, we'll do that for the right side. That's a good one for the right. How about for the left, though?
Oh, I'm sorry, I'm thinking in opposites. It would be negative 2.01.
Yeah, let's try negative 2.01. Negative 60. It's heading down. Okay, so when you are to the left, you're way down there. All right? Now let's check to the right. Okay, negative 1.99, that's a good value. We're up at positive 59. Okay, we're way up. So that's approaching positive infinity. Okay, so when we're at negative 1.99, we're way up there. Right, now we're going to do the same thing again. We're going to check to the left and the right of the other asymptote. Hey, how about, Carly, what would be a good value to the left of the asymptote at 3?
2.99.
Yep, 2.99 would be good to check. Okay, we're at negative, it's a little hard to see. It says negative 40. In other words, it's pretty far down. Okay, and now let's check a value to the right of it. So let's check 3.01. We're at 40.12, so we're way up here again. Right, and if you remember our horizontal asymptote, it's getting closer and closer to 0. So let's try a big value. Let's try like 50 for x. Just a little bit above 0. So when you head way out to the right, you're just a little above 0. And when you head way out to the left, you're just a little below 0. Okay, all of those points give me enough information to sketch the graph. This graph is in 3 pieces. Okay, there's going to be a curve in the lower left section that has to get closer and closer to that green line. So something like this. That's that section. Okay? It's very similar in the upper right. We know we have a point way up here, point way over here, and we can't cross those asymptotes as we start to head towards infinity. Sometimes we cross them near the origin, but not towards infinity. Okay, so this part, something like that. Okay, now the middle part. The middle part, we actually have quite a bit of data. We have 4 points, and we have to connect the top all the way to the bottom. Now, everything here is a smooth curve. Nothing turns sharply. right? So you're getting closer and closer as you head towards that point. Oops, we're coming down through those points, and then I have to start getting closer and closer to the other point. And that's our sketch. Okay, let's just confirm that by graphing it, see how we did. Pretty good. I'm not going to be overly picky. It does look like theirs is a little flatter than mine was here. So maybe I should have made it a little bit flatter. But the important thing is you've got all three sections of it, and that I would say that's pretty accurate. Okay? And that's how you sketch a rational function. We'll try another one or two. Question? Yes?
What was the equation that you plugged in?
The equation? I used the one that was unfactored.
Okay.
But if you do the factored one, it should come out the same.
Okay.
Any other questions on that? So once you find your asymptotes and then investigate on each side the behavior, it's actually not that hard to sketch, even though it looks like it could be a hard graph to do. All right, so this one's a little bit different because look at the leading terms. Now the exponents match. Okay, when the exponents match, that's going to affect our horizontal asymptote. It's not going to be the same as what it was before. All right, let's take a look at that denominator. What can you factor out of the denominator? Okay. You can take out an x, and that leaves you with 2x minus 5. Keep both versions because they both come in handy. Now we'll find our vertical asymptotes. Can somebody give me just one of the values that if you plug it into this denominator, it would cause it to be 0? Yeah?
2.5,
Okay, and how did you get that?
because if you multiply 2 times a number and subtract 5 from it, it has to be 0.
Yeah. Okay, so if you set 2x minus 5 equal to 0 and you solve it, you'll get 5 halves, or 2.5, and x equals 0. Now, the one thing we do need to check is to make sure we have no common factors, okay, in the numerator and denominator. All right, and you can try to factor that, but it will not factor with anything that's in the denominator. Just if you want to try it, you can, but just trust me. Okay, so there's your vertical asymptotes. Okay, what's our end behavior model here? Let's do that, and then we'll do the horizontal asymptotes. Brian?
It's 3x squared over 2x squared.
Yeah, it's 3x squared over 2x squared. The x squareds are going to cancel, and we get 3 halves. So what happens to the fraction 3 halves as x gets really, really big? It just stays as 3 halves. Okay, so the asymptotes kind of give you your boundaries, okay, of where things are going to happen. X and Y-intercept. Okay, let's see. So to find our, let's start with the Y-intercept. That one's actually pretty easy. To find the Y-intercept, just let x equal 0. Okay, so in the numerator you'd have 0 plus 0 minus 4 over 0 minus 0 is 0. So what's the Y-intercept? There is no Y-intercept. Because the problem is the value that would make, the value that you would need to use, okay, when you plug 0 in, that's how you find your intercept. But you can't use 0 because it's a vertical asymptote. That's an undefined value not in the domain. So there is no Y-intercept here. This graph will never cross the Y-axis. Okay. Now we can still check for an X-intercept. Yep.
So when you say there is no Y-intercept, that means that it's not a Y-intercept.
Well, it means when I sketch the picture is never going to cross the y-axis. So this one did cross the y-axis right at 1/6. This one won't. Okay, and to get your x-intercept, that's a little bit trickier. Right, to get the x-intercept, what we basically have to do is, actually that numerator does factor, because you have to find the zeros of the numerator. That's the only way you can make the fraction 0. But I think that does factor nicely. X minus 1 and 3x plus 4. Does that work? It's 3x squared plus 4x minus 3x is 1x. Yeah, that's good. So now we can actually find the roots of the numerator easily. I thought we were going to have to use quadratic formula. That was going to take a while. Okay. So x equals 1. It's going to cross the x-axis there. And it's going to cross the x-axis at negative 4/3. So it's going to cross the x-axis twice. 1. Actually, let me try to draw it because they're very close. 1 and like 1.3 repeating. All right, so we got that?
Negative 4.
Oh, yeah, thank you. Yeah, negative 4/3. So that actually makes it easier. Okay, so we got our x-intercepts. Let's draw the vertical asymptotes at 2.5 and 0. So there's 2.5. There's 0. And what's our horizontal? 1.5. Yeah, a lot of rational functions that we're studying have this behavior where you get kind of like a curve shape in the middle, and then you get something bounded in the upper left and upper right, or some combination of sections of this grid. Okay. So to figure out where we're going to be, let's type it in and check what happens to x. So we have 3x squared plus x minus 4. Divided by, let's see, 2x squared minus 5x. All right, so I want to check the behavior on each side of the vertical asymptote. Okay, let's start with 2.5. What would be a good number that's just a little bit smaller than 2.5? Yep.
2.4?
Yeah, I may even go really close to it, like 2.49, but negative 300 something. Okay, so when you're to the left, you're down at negative infinity. Let's check to the right. Let's try 2.51. Positive infinity. Let's check to the left of the vertical asymptote at 0. So that'd be like negative 0.01. Okay, we're way down at negative infinity. And let's check to the right. Up at positive infinity. And you can check what's going to happen as you let x get really big, but I guarantee you it's going to be right there. It has to stay under that asymptote. It's not going to cross it as it gets really big. And up here, since we're starting here and we're going to come down and curve, it's going to have to just stay slightly above it. Okay, so very similar picture to last time. Okay, there's one section. The middle section is going to do just what it did last time. So it's going to come down, curve, keep going. I don't think it's going to be as flat this time in the middle. And then this section, like that. Okay, let's graph it and see how we did. Yeah, it's pretty good. When the graph starts to get really vertical, the calculator has a hard time with it, but that's how it should look. Okay. Any questions on that one? All right, so let's see. That one and that's it. Okay, why don't you give this one a shot on your own. Okay, this will be our last one, but try it, see if you can sketch it. If you get stuck, let me know, I'll come over and I'll help you out. All right, so first thing I would do here is look at the denominator and see if it can be factored. If it can, that's going to make your vertical asymptotes a lot easier to find. Is anybody able to factor the denominator? Carly?
I got x plus 1, x minus 3.
Okay, let's check. X plus 1, x minus 3. So we get x squared minus 3x plus 1x is minus 2. And 1 times negative 3, negative 3. Yep, so that's good. All right, so now let's find let's start with our intercepts. Okay, the x-intercepts. Okay, what's the x-intercept here? So remember, you'd be filling in a 0 on this side to somehow make the fraction equal to 0. What would do that one, Random? 2. It's going to cross the x-axis at 2. Okay, so we get that. Y-intercept. Just fill in 0 for x, but if you end up dividing by 0, you can't have that. So in this case, we get 0 minus 2 over 0 minus 3. Those cancel. There's my y-intercept, 2/3. Okay, so y-intercept, x-intercept. Let's find the vertical asymptotes. Okay, there doesn't always have to be 2, but in most of the problems we've done, there have been. Okay, what's the 2 vertical asymptotes here? Yeah, go ahead.
3 and negative 1.
All right, so 3 and negative 1. Yep. So put in a vertical asymptote of 3, negative 1. Can I probably already guess what's going to happen in the middle? We're going to have that kind of curved shape. All right, now let's put in our horizontal asymptote. So let's find the end behavior model. Okay, in this case, it's x divided by x squared, which becomes 1 over x. What's our horizontal asymptote here? Well, Micah? What's our horizontal asymptote?
0.
0, yep. All right, so let's look at what happens on each side of the asymptote. This is where it's helpful to plug it in. So we get x minus 2 divided by x squared minus 2x minus 3. X squared minus 2x minus 3. I'm going to check just to the left of negative 1. So what would be a good value to the left of negative 1?
Negative 1.1.
Sure, negative 1.1. Okay, it's at negative 7. If you can't tell from that, it is heading down, but try something really, really close to it. Okay, now you can see it's way down. Okay, negative 75. Okay, on the other side, just by what I've already graphed, I can tell it's going to be positive, but if you're not sure, just try a point. It's way up at positive infinity. Okay, now when we check just to the left of 3, let's try 2.99. It's going to have to be down at negative infinity. If it wasn't, I don't think our graph wouldn't work out correctly. Okay, but let's just check to make sure. Okay, it is at negative infinity. And lastly, check 3.01. Okay, positive infinity. Okay, we're bounded, we're trapped in that part of the grid made by the asymptotes in the upper right, and the same in the lower left. And it's very similar to what we've had before. Got that part. That part in the middle. So this time, I think in the middle, you are going to see more of a turn versus it being like a smoother curve. And let's check our graph. That's pretty much what we got. So any questions on graphing rational functions where the degree in the numerator is less than or equal to the denominator? Tomorrow we'll look at what happens when it's not less than or equal. All right, so the homework on page 234. Okay, it is mostly graphing. Some non-graphing questions. 1 through 7 odd. 9 through 12. 15, 17 to 22 odd, 17 to 22 all, sorry. 23 to 26, 29, and 33.